Good morning and welcome to this CPD webinar entitled Putting the IoT in Engineering, the second in our four-part series of webinars on the theme of emerging trends in engineering. My name is Aidan O'Flaherty and I am the CPD Associate Director here at Engineers Ireland, and I'm joined by Amanda Greville from the CPD team who will be managing the webinar from behind the scenes. I'd like to thank you all for joining us this morning, and I hope everyone is keeping well. So while we are waiting for others to join the webinar, feel free to use the chat function and to say hello and perhaps let us know where you are this morning, at home or in the office, in Dublin, Cork, Limerick, Donegal, or perhaps overseas. Firstly, some housekeeping. Hopefully you can hear and see me okay. If you have an issue, can you use the chat function to let Amanda know and she will try and resolve it. We will reserve the Q&A function for questions. We plan to have 20-25 minutes for Q&A at the end of the module, but please feel free to enter your questions as we go along. If you happen to lose connection or have any technical difficulties, please use the chat function or contact the CPD team by phone or email. At the end of the session, when you leave Zoom, you will be directed to an online survey, and we would be grateful if you could take a few minutes to complete it. We really value your feedback. We will provide a PDF copy of today's presentations after the webinar. We are recording the session, which will be made available on the Engineers Ireland website in the coming weeks. We won't record the Q&A, or we will edit it out in any case, so feel free to ask all those difficult questions. The webinar counts as 2 hours towards your annual CPD requirement, and if you registered online, you will find the session in the attended events section of My Events on your profile. And if you click on confirm attendance, the activity will automatically be added to your CPD record. Okay, let's move on to today's session. As an emerging trend in engineering, we really can't ignore the Internet of Things, machines sharing data, as this is at the heart of the fourth industrial revolution of digital automation and makes artificial intelligence and data analytics and robotics and automation all possible. And the aim of the session is to give an introduction to what the Internet of Things means and an introduction to the variety of ways it can be utilized in engineering projects. And the session wouldn't be possible without the collaboration of the Nimbus Research Centre at MTU, Munster Technological University. And I would like to thank at the outset Professor John Barrett and his team, including Heba Almaleh and our speakers, Christian and Anne, for their time and expertise. We have collaborated on a number of CPD initiatives to date with Nimbus, and the feedback from our members and our client organizations has always been excellent. So let's look at the program for today. We will begin with a presentation from Professor John Barrett with an IoT overview for engineering. We will allow for some questions after John's presentation, as he will be leaving us before 12. So we will give you the opportunity to ask John any questions before he leaves. Christian O'Leary will then deliver his presentation on data analytics and visualization of IoT engineering data, followed by Quang-An Fan on data analytics applied to real-world research and industrial applications. And then we will have a Q&A session with Christian and Quang-An. So I'm going to introduce John and then stop sharing my screen and allow John to share his. So John Barrett is Head of Academic Studies at the Nimbus Research Centre, where he manages the academic activity of the centre. John's research area is the miniaturization, packaging and reliability of embedded wireless serving systems, particularly for operation in harsh and rugged environments. He is a member of the CIT Postgraduate Research Board, where he has acted as chair, the CIT Academic Council and the CIT Research and Innovation Committee. He is an academic research associate of the Tyndall National Institute, and John has delivered keynote and expert presentations at events across the world, and his TEDx CIT talk on the Internet of Things has over 500,000 views. So we're going to add a few more views to that, John, so I'm going to pass over to you now.
Thanks, Aidan. Giving this the broad title of the Internet of Engineering Things, because we have an engineering focus. The broader term is Industry 4.0. And even as we talk about Industry 4.0, we're heading for Industry 5.0, which is human-centric industry automation. But more broadly still, I would call this simply data-driven engineering. And there's an argument to be made, certainly, that engineering always has been data-driven. We've always measured, we've always monitored, we've always analyzed the measurements, and based on the analysis, we go back and do control, or we fix things, or we adjust things. The difference now is that we have wireless connectivity everywhere. We have low-cost microelectronic sensors that can measure anything. So we can measure anything, anywhere, and we can send large volumes of data through high bandwidth connections. And when you combine that capability with the availability of low-cost, high-performance computing from anywhere from our fingertips up to the cloud, then you get the ability to collect, analyze, interpret, and act on very large volumes of data from anything, anywhere, anytime. And that is the Internet of Things. And I have a video that I've been showing now for, it must be 8 or 9 years since this video came out, but I still use it.
There's a whole new internet at work. Machines communicating with machines, sharing a wealth of data seamlessly, tirelessly, behind the scenes. Forget real time. This is between time. Machines moving industry forward at lightning speeds. Welcome to the industrial internet. Out at sea, a large cargo ship traverses the giant waves, carrying parts destined for a far-off wind farm. Tiny sensors throughout the engine ensure everything is working properly. They report back on propeller performance and power output. Other sensors above deck monitor the ship's precious cargo and confirm its condition and safety. The ship's tracking data determines the destination and arrival time. Everything checks out. The cargo is now traveling securely aboard a hybrid evolution powered freight train. Inside the cabin, the engineer calls up a status report on the entire train. Real-time slows. Between time, a vast universe of data is collected and interpreted. In the blink of an eye, sensors calculate engine temperature, fuel efficiency, speed, weight, and vibration patterns. At the same time, sensors in the track relay the train's location to the network, where information from all other trains comes in. This gives the network the ability to coordinate movement and optimize efficiencies throughout the entire system. And our train remains on schedule. Meanwhile, at a nearby wind farm, a new turbine powers up for the very first time. Within seconds, tens of thousands of data points are analyzed, and the farm controller delivers operating instructions to the turbine, bringing it up to speed with the rest of the farm. Leveraging thousands of hours of stored data, the farm automatically calculates how to increase and decrease individual turbine output. The turbine can tailor the pitch of its blades to capture just the right amount of wind. As the farm responds to the demands of the power grid, it delivers energy as instructed. Next, the grid carries precise amounts of energy to a network of local charging stations. Drivers can charge up and head home. This is the industrial internet. Brilliant machines, providing the insights to make better decisions.
This was a concept video from GE in the early days of the industrial internet. And the reason I still show it is that everything in it now is operating in the real world. It had excellent foresight. And to take a real example from our own work with Nimbus, we engaged with the Irish Navy and particularly the LE Samuel Beckett. And they gave us access to their engine room. And we fitted a network of these sensor modules across the various bits of machinery inside and around the engine room. It's a multiple sensor module. It had an inertial measurement unit for doing shock and vibration. It had a microphone for listening to the sounds of the machinery. It could measure humidity and temperature. And we put a network of about 15 of these in the engine room. We weren't allowed, for security reasons, to actually transmit data from the ship, but the ship went on a 2-week deployment and the network collected data for the 2 weeks of the deployment at sea. And we collected all that data. And there are a number of ways in which you can view and make use of that data. We can do the old-fashioned engineering way and simply draw a graph. In this case, temperature humidity map from the engine itself over about 16, 17 days of the deployment. We can, what I would call as a meaningful data presentation, which makes it easier to identify anomalies. So a vibration frequency spectral graph showing both the frequency and the amplitude of the vibration. And we can see on day 8 that there's something unusual. And there's a 5G shock on the gearbox on day 8. Now, the gearbox didn't suddenly jump off its mountings, and the reckoning with the engine room crew was that the stern of the ship dropped into a very large wave trough and slammed into it. But when you can present the data like that, it makes it easier not only for humans, but also for the data analytics algorithms to identify anomalies and flag them. You can also make use of the rapidly growing technology of extended reality and virtual reality and augmented reality to superimpose data on the systems that you're looking at, again, making it easier for humans and human engineers to see where anomalies and problems are starting to happen. We can hand over some autonomy to the data collection and analytics system to tell us just what I need to know so that we don't get overburdened with information. So on the bridge, we can have a data analytics and machine learning system that only flags anomalies that the crew need to know about based on preset protocols. You can go down the road towards full autonomy, and the industrial robotics, autonomous vehicles are probably the best known example of that. And if we carry on with the taking the nautical analogy we've had since the beginning, there are concept ships like this one from Rolls-Royce, which are fully autonomous. But in any context, partial or full autonomy can't happen in isolation. The Port of Rotterdam wants to be able to accommodate driverless vessels by 2030, but the whole port technology network has to be geared up to be able to manage that, and not just the technology network, but the entire port management and organization system has to be transformed to be able to handle these vessels. And while the Internet of Things offers the possibility of heading towards a very high level or even complete autonomy in many engineering applications, there's a lot of preparation, both from the technology point of view and from the business organization point of view, to be able to go down that road. And very often with the Internet of Engineering Things, all we'll simply do is monitor. We'll collect data from wherever we want to collect it from. But if you combine the collection of data and a lot more data than we have been able to collect previously, with strong data analytics, you can get into the area of PHM, prognostics and health management, so that you move from scheduled maintenance and even preventative maintenance to getting early warning of when problems are starting to develop in engineering systems. Now, again, there's a lot of analysis and research required to be able to identify when an anomaly is something to actually worry about, but the potential is there. You can, as we always have done in engineering, move to monitoring and control in a feedback loop. The difference being that we can collect a lot more data and control a lot more things and do more sophisticated analysis and control many things in real time. And as I mentioned earlier, you can go down the road of gradually increasing autonomy. But I've sometimes used the analogy that autonomy, handing over autonomy, is like letting your teenage children go off and be independent. You've taught them how to behave. You will trust that they will behave properly, but you would be able to like to check that their behavior matches your expectations. And so in the area of autonomy and automation, the concept of digital twin is a growing one, where you have a computer-based model of the system that you're monitoring and controlling, and you match the behavior of that model with the measurements that are coming from the real system. And so building digital twins, and they could be simple computer models, or they could be more sophisticated extended reality models, and matching up that modeling and simulation with the analytics and with the control is one of the major areas of development for the engineering IoT. But as I mentioned from the beginning, the Internet of Things is all about data, collecting that data, interpreting it, and acting on the data. And if I went back probably not much more than 5 years, this is what the data chain would have looked like. You have your sensors, you have your wireless Internet of Things nodes, and you transmit the data up to the cloud for analytics. Now, that causes a problem, particularly if you need real-time and fast monitoring and control systems, because the transmission to the cloud and back can introduce a significant lag. So the modern data chain distributes the analytics all the way down to the IoT nodes themselves. So some analytics done, embedded analytics done on the IoT nodes. At the edge, where you're beginning at the very edge of the systems you're collecting data from, you begin aggregating some of the data and doing embedded edge analytics. And then there's what's called the fog, which might cover an entire, say, factory installation. And you begin to aggregate data at the factory level. And then you head up into the network and into the cloud for more sophisticated analytics and dashboards and areas like that. Again, in the last 5 years, we've seen a very strong growth in machine learning. And if you went back only a few years, machine learning was confined to the cloud because the computing resources required to do machine learning were so large that you couldn't distribute them down to the other layers of the data chain. But again, evolutions in computing and in machine learning algorithms mean that machine learning can now be distributed all the way along the data chain, and you have the capability of doing edge data analytics with embedded machine learning algorithms, which increases the sophistication of real-time monitoring and control and increases the capability for more sophisticated automation and handover of autonomy. And so you get a multi-layered data chain where you have different capabilities. Down at the edge and down at the thing that you're monitoring, you have the capability to do protection and real-time control systems. And as you go up through the data chain, through the edge, through the fog, and up into the cloud, machines can begin talking to each other. And I use the term machines very broadly in terms of engineering things. Machines can start talking to humans, and you can begin to aggregate data across systems. And that is where the real power of the Internet of Things begins to come in, where it's not just looking at individual machines or things, but you're looking at aggregating data from whole manufacturing, production process, civil engineering systems, critical infrastructure, areas like that, energy systems, water systems, and so on. And you go all the way up into the cloud then for accumulating business intelligence that can drive business forecasts and longer term business decisions. And fundamentally, with all those capabilities, there is nothing conceivably that we cannot measure, monitor, and control across the engineering world, no matter where it is, no matter what it is. And there has to be challenges. It can't be that easy. And I want to summarize what I would regard as the main high-level challenges you have to consider when you begin using the industrial Internet of Things. As I say, you could do almost anything. But the question is it worth doing, and where is the business value? And I've mentioned autonomous vehicles and autonomous systems a few times. And in the civil engineering business, you'll see a lot of hype about autonomous things like excavators and loaders and other areas like that, fully autonomous ones that will transform civil engineering operations. But you need to ask the question, when is an autonomous excavator faster or safer or cheaper or more reliable or more efficient than an excavator with an experienced operator? And that is a complex calculation to identify where the engineering value is and the business value. Is there a case that it would be much more efficient to simply augment the human operator with a head-up display or a windscreen display on the excavator that feeds in data from the excavator, from the area to be excavated, from the cloud, which is guiding the excavation, and combine the irreplaceable skill of a human with the augmented technology? You may identify that something is actually worth doing, but then you have to ask yourself, is it actually possible? You can measure anything, but can you make sense of the data? So taking the very old example of wheel tappers, they had a wealth of experience. They could tap the wheel and tell whether it was ringing more dully than it should. We could replace the wheel tapper with a whole network of sensors. But how do we interpret the data coming from those sensors to actually say that, hang on, this wheel is having a problem? The metal is beginning to fatigue, the bearings are beginning to loosen. There's a wealth of research that needs to be done to be able to interpret the data and to identify the anomalies. And it may not be sufficient simply just to measure the wheel. You may have to measure the whole suspension system for the train bogies to be able to fully interpret the data. And then you're looking at a whole complex set of data coming in from different parts of the train assembly, and the challenge of making sense of that grows. So whenever you start to measure something, you have to take into account, how am I going to actually interpret the measurements to give me something useful to act on? So where do you stop in terms of doing your measurements? Again, going back even 5 years, connectivity for collecting the data would be a concern. But we now have a wide range of dedicated Internet of Things data collection networks designed to collect the data from large numbers of geographically dispersed objects. So connectivity in the vast majority of applications is no longer a problem. And even for the most remote areas, we're seeing the growth in satellite clusters, taking Elon Musk's Starlink as one of the examples, which is delivering connectivity even to the most difficult and remote areas. But I would say that one of the biggest challenges is it safe to do it? Fundamentally, anything that is wirelessly connected and uploading data to the cloud is hackable. So I would say the first consideration, or not the first consideration, but among the first considerations that have to be taken into account is, how am I going to keep all this secure? And it's not just secure in terms of being hacked, but it could also be secure in simply having valuable engineering, process, manufacturing data stolen. So how do you keep data sets private when you're transmitting them all over the place? And we have seen a number of high-profile hacking, successful hacking attempts in recent months. And probably the one that's most relevant to the IoT was the hacking of the Colonial Pipeline on the east coast of the US, which caused massive disruption because their control system was connected to an internet-connected computer. But we also had, say, more minor incidents that may have not reached the same publicity, such as the Tampa Bay water system in Florida, where a hacker got very close to injecting large amounts of sodium hydroxide into the water system. We have to be very, very careful, and security and privacy and data integrity have to be primary concerns. And all the technology allows us to collect oceans of data. And the real challenge is extracting meaning and value on it so you can act on the data. Collecting data is useless unless you can get some value out of it and act on it. And there's a lot of hype around machine learning and artificial intelligence, and they can do a lot, but they're not the magic that the hype will often claim them to be. They're powerful, but they do have their limitations, and it's important to understand them. But having said all that, there is huge value to be got from the engineering Internet of Things. I guarantee that everybody here in the seminar either is or will be using IoT technology before long. And every engineering business, every engineering organization, every engineering operation is going to become more data driven. And the difficulty quite often, and it tends to come from the tech industry who are selling the technology for the Internet of Things, is separating the hype from what's really possible, and more importantly, separating the hype from what's useful from an engineering point of view. And it's important for any organization launching down the Internet of Things road to get unbiased advice. And we're lucky here in Ireland because we have a number of sources. Enterprise Ireland operate a network of technology gateways called the Applied IoT Cluster. It's a gathering, I think, of about 7 or 8 of the technology gateways around the country, specifically focused on different aspects of the IoT. And they're an excellent resource for unbiased advice. There are also a number of Science Foundation Ireland research centres who would be in the area of the IoT. 2 of the major ones that would be relevant for engineering applications would be the Connect Advanced Networking Research Centre and the Confirm Research Centre for Smart Manufacturing and Engineering Applications. Thank you very much. If anybody has any questions, I'll be pleased to try and answer them.
Thanks a million, John. As ever, an excellent presentation and a very measured analysis of the merits of IoT. As you say, it's not always the panacea, so you have to assess whether it's worth doing, whether it's possible, whether it's safe, etc. before deciding to embark upon an IoT project. But it is inevitably coming down the line. I'll kick off with a question for you, which when I introduced you, we spoke about the fact that some of the research work that you've done has been looking at embedding systems into remote and harsh environments. I was wondering, what are the considerations that need to be taken into account with those environments, perhaps compared to let's say a more benign environment like a clean room or a manufacturing site?
I guess if you work your way up the levels of the data chain, the hardware has to be robust against whatever environment you're putting it into. So that could be a case of, it could be that you're measuring physical parameters, which may involve heat, vibration, mechanical stress. And you can certainly measure them, but if the overall measurement system isn't robust in the environment in which you're placing it, then you have a problem from the beginning because the hardware will break.
Yeah.
It could also be that the hardware is, you could be looking at a chemical or biological measurement. And so the front end of the hardware has to be robust against whatever materials it's in contact with. And there's a large movement towards non-contact measurements, particularly say optical and spectroscopic measurements, because there are now even systems for deploying sophisticated spectroscopic measurements in embedded systems, small electronic systems. Going up the chain, if you consider an average, say, industrial environment, there's a lot of electrical noise, and the networking starts to become a bit of a problem. So if you have a lot of electrical noise around or a lot of metal, then the transmission and collection of the wireless signals becomes a bit more of a challenge, but that can certainly be managed. And then it's you have the whole area of, once you start transmitting the data, it's not exclusive to the harsh environments. If you're very remote, it has always been a challenge to collect the data. So we have work that is looking at sea states off the south coast to be able to look towards, begin to say, how's the sea state changing and how will that match up with tides and weather forecasts to predict flooding and tidal surges, areas like that. But collecting data from a radar on a very remote place on the coast, where you have a high amount of bandwidth, is difficult because you don't have the upload bandwidth for the data. So in that case, having the embedded analytics at the radar to be able to filter down the data and only send up things that are significant and that show anomalies is the important thing to do. And again, it can be the same in many harsh environment applications, that you can't get the data out fast enough. So being able to do the analytics at the edge is very valuable from that point of view. And then the overarching one in any application, if you're working in harsh environments, you may often be talking critical systems, because you wouldn't be measuring and trying to control in a harsh environment unless you were perhaps looking at something. If it's a critical failure, you could have serious consequences. If a high temperature system fails, or you're monitoring a bridge in a remote location, anything like that. If a chemical system is starting to fail, a chemical manufacturing process, the consequences are obviously could be very severe. And so then you have to be looking very much at the data integrity. And so it's often, security is not often always about data theft. You could simply have somebody interferes with the data. So you have a gas distribution network or an oil distribution network, and they interfere with the data chain to say everything's fine. And at the same time, they're hacking into one of the remote control valves and hiding that fact from you,
Right.
and making the valve look normal.
Yeah.
And that's the level of sophistication we're looking at for the hacking that can happen. So all those sort of fall in under, I guess, what I would call the harsh environment and demanding. Harsh is often a case that of difficult, in that if you're looking at a national gas distribution network, you have a national network of data collection, and ensuring the integrity of all that is a big challenge.
Okay, that's great, John. Thanks for that.
No problem.
We have a question from John Coleman. So John is a very active member of the META Society, which is the Irish Asset Management and Maintenance Society. So he, first of all, he says, very interesting presentation, and he thanks you, John. His question is, assuming technology continues to evolve as you have outlined, are we likely to lose the necessary skill or skills to operate the systems should there be a technical failure, or will the equipment be so technical it will not work at all?
It is something I've considered and have lots of debates about. First of all, no matter what the hype is, we're never going to replace people. Certainly, even the youngest person on this seminar, I don't think within your lifetime that we're going to see artificial intelligence that any way approaches human capability. I'm not even sure within our lifetimes we will even have an understanding of how our brains work. So I think that the human in the loop will always be necessary. And it will always be necessary because humans design the machines. We will always have to, we cannot design something more complex than we understand ourselves, is my theory. Mm. And that whatever artificial intelligence we program, we have to look at, we have programmed it. And it's going to be a very, very long time before any artificial intelligence can become more intelligent. And there's a difference between intelligence and training. You can train a dog, but its intelligence will never improve. It will do more things and will learn to do more things, but its fundamental level of intelligence never changes. Mm-hmm. And I think that is the limitation in artificial intelligence. It will never be able to improve its own intelligence. Only humans will be able to increase the intelligence of artificial intelligence. And in that case, whatever systems we develop have to be comprehensible by humans. Mm-hmm. Now, there's a danger, the main danger, I think, is that, and I think it could be self-limiting, that systems become so complex that a smaller and smaller number of people can understand them. And so you're then looking into a talent roadblock, mm-hmm. where you can't get enough talent to be able to deal with the machines you're buying and implementing. But I think that in itself will be self-limiting. And I have another theory, and I'll let you go then because I could talk all morning. I think that we are already creating systems of such complexity that, and which have outrun regulation. And certainly in the engineering field, regulation is key. And we have seen with the current internet and many of the social media platforms that their capabilities have outrun regulation, and we've seen chaos ensue. And I think in engineering, regulation, because we're so used to being regulated and that nothing's released on the market or approved for use without it being regulated and meeting standards, we're in a better position than, say, the open internet for delivering systems that are trustworthy and safe and properly regulated, and not so complex that we can't actually trust them.
Okay, so there's some light on the horizon there.
I would say so, and certainly in engineering.
Yeah.
We're in
Yeah.
a different domain than social media platforms.
Yeah. Brilliant, John. And we are going to let you go because I know
Okay.
you have another meeting coming up, but thanks a million for that. And I just remind the audience as well that you authored an article in the Engineers Journal back in, I think it was November of 2020, which also kind of addresses the Internet of Things and some of those kind of technical, practical, and even philosophical questions that arise when we discuss this topic. So I would recommend that to anybody who wants to read it a little bit further. So thanks once again, John.
Thank you, Aidan, for the opportunity, and thanks for everybody in the audience.
Pleasure.
Bye.
Take care now, John. Okay, so that brings us on to our second presenter today, who is Christian O'Leary. And Christian is a senior researcher in AI at the Nimbus Research Centre with interests in machine learning, optimization, and multi-agent systems. Christian has worked on applications involving computer vision, forecasting, anomaly detection, chatbots, sentiment analysis, and schedule optimization. He has been a principal investigator managing some of Nimbus cybersecurity projects. He has completed an MSc in AI from CIT in 2020 and a BSc in computer science at UCC in 2017. And he has previously worked in Johnson Controls as a software engineer. So I'm going to hand over to you, Christian, if you want to start sharing your screen.
Yeah, okay. Thanks, Aidan.
Great.
All right. Are you able to see that okay?
Yeah, we can indeed.
Perfect. All right. Okay, so as Aidan mentioned, I'm a senior researcher in Nimbus. I work in the software and data analytics teams. And the projects that I typically work with are software projects with a very heavy AI element. And this project is going to be data analytics and, sorry, this presentation is going to be data analytics and visualization. Okay. So just to give you a brief outline of how the talk is going to go, we're going to briefly introduce data analytics at a very high level, and I'm going to mention some of the steps involved, like how do we handle data, how do we store it and visualize it, how do we apply models to data, and how do we get those models into a live environment. And finally, we're just going to go over a couple of use cases, and the next talk is going to go over some of those use cases in a bit more detail then. Okay, so what is data analytics? Data analytics involves examining the raw data that you have available to you, and it could be any kind of data. It could be sensor data, social media activity, stock prices, whatever you have available to you. The process is actually going to be fairly similar regardless of the domain. You gather the data you have available to you, and then the first step is going to be to examine that data in detail. So you need to understand what kind of patterns and trends are prevalent within that data set. And based on that, then you can decide what kind of modeling you want to do and what goal you can set goals based on that. Collecting the data and preparing it is actually probably going to be a very large chunk of the time and effort that goes into a data science project. For most of them, that's actually a fairly large chunk of the budget as well, because that is something that you're probably going to do iteratively. You're going to get a first iteration of data, you're going to examine it, and then you're going to need to clean that data and make it consistent in a way that you can apply models to it. Actually, writing code for modeling isn't that time consuming in itself, although running models can be extremely time consuming depending on what kind of models you want. So statistical models, you can fit them pretty much instantly. Machine learning models can take weeks or even months depending on how large your data set is and what kind of training you want to do. Once you have your models in place, you're going to evaluate them based on some domain-specific metric, and then you're going to iteratively refine your models based on that until you're happy with what you get, or at least until you know you're not going to get anything better. Once you have your models trained and ready, what you can do is you can deploy them and let them out into the wild. So this process is somewhat domain agnostic in a lot of the steps that you're going to be carrying out, but just to give you some examples of what the applications are. One application is predictive maintenance. So this would be trying to predict when your machines are going to break down and when to schedule repair or replacement, as opposed to simply reacting to the breakdown when it occurs. Anomaly detection is popular with a lot of our clients. Anywhere where you have time series data, whether it's sensor data or social media activity, anomaly detection is often a very useful way to gain insights into what you have and to give you alerts. Forecasting is another popular one. So we've done projects on electricity price forecasting, milk yield, and social media activity. Sentiment analysis, what that means is when you try to analyze usually textual information, but sometimes image and audio information as well, and you try to estimate what is the sentiment behind that activity. So this is especially popular with projects that involve social media data. So the idea is that if people are writing, let's say, about your services, are what they're writing mostly positive, or is it mostly negative, or some other range of emotion? We also do projects on recommender systems. So when you buy something on Amazon and Amazon gives you recommendations about what else you should buy. So our customers also liked this product. That's what recommender systems do. They try and build relationships between different entities so that you can usually display those to your clients. So once you have a source of data identified and you have some goals set, you need to decide how you're going to store your data. So you might start by working with some file-based format, like working with Excel, and that's okay if you are happy to work with a fairly small snapshot of data. It can be very convenient to work with, and it's good in certain contexts, but it's also very, very limited. The data is static. You typically have a hard limit on the number of rows that you can have in your Excel sheet. Big problem is version control as well. People working with different instances of the same document. So if you're backing up different versions, you probably need to make sure every person is using the same version as you are. A big concern as well is data integrity. So if somebody enters in data and they do it in a format that's incorrect or in a format that's inconsistent, usually that information is there to stay. So you've effectively corrupted your data set to some extent. So Excel sheets, they're not really designed for very large numbers of users or for very large amounts of data. So if you're working with large data sets, or especially if you're working with live data, you're going to need to use a database at some point. So databases, they're higher performance, they're perhaps a little bit less accessible for people, but they are far, far more accessible for software, which is really important. Databases, they also check the integrity of the data that you have. So if somebody tries to enter in data in a format that violates the constraints of your database, that action is going to be rejected. So it ensures consistency within the data you have, and that's really important for being able to model your data. So just to give you an example of where things can go wrong with formats like Excel, last year about 16,000 COVID cases were lost over in the UK because they were using an older Excel format. Now the newer Excel sheets, they can store a lot more data, but you still have that hard limit. And if it's a very large data set, that's a very serious problem for you. So this older format, they were only able to store about 65,000 rows of data, and anything else they added beyond that was simply lost. Once you have your data in a secure location, somewhere like a database, I mentioned that it's easier for software to integrate with that. So just to give you some examples, there's a lot of visualization tools like dashboards that you can connect to a database. So this is just one example. It's called Grafana. It has a free version. It's a drag and drop configurable dashboard. You can select what kind of visualizations you want, and you can select how often you want that to be updated. So what these dashboards will do is that they'll poll the database and they'll show you data periodically or almost in real time. And based on what it is you want to show, you can select different kinds of visualizations and you can customize them to make them more readable. So that's a really, really useful way of understanding the data that you have. For some of these dashboards as well, here's another example called Cabana. A lot of them have built-in very simple anomaly detection tools, very simple analysis tools, and they can send you email notifications if the data source stops producing data, or if you're getting very irregular data. Although the anomaly detection they do tends to be somewhat simple. So once you have your data in place, a large amount of effort for any data science project is going to be in cleaning the data that you have available. So for example, if we had, let's say, a time series data set, you're going to want to decide how you handle gaps within that time series data set. So gaps can happen because sensors stop working or because of time zone differences. So for example, if the clocks change by an hour, you'll often end up with data sets where you just have 1 hour randomly missing every year, and you have some instances where there's some overlap as well. Depending on what you want to achieve, you're going to also need to decide how you handle very weird or anomalous behavior. So if we're doing anomaly detection, we obviously want to keep outliers and strange behavior because those are the focus of our research. But if we're doing something like forecasting, we're probably going to want to remove or replace that data because that's going to confuse the model that we're trying to fit. So the type of pre-processing we do depends on the data we have. If we're working with something like images, what we'll do is try to make those images the exact same format. So if we develop a model that works with images in a 256 by 256 pixel format in grayscale, every image we feed into that model has to have that exact same format. So we need to resize them and convert them to grayscale. If we're working with text information, we can feed that into a model as well, but there are some extra hoops we need to jump through. So statistical and machine learning models, they only work with numerical data. So what we're going to have to do in that case is convert our text into some numeric format. And before we even do that, we're also going to need to clean it, especially if the text is coming from humans. So if the text is coming from a machine or from some error logs on a server, you can expect the text to be fairly consistent and show more or less the exact same thing every time. With humans, there's spelling errors, grammatical errors, hyperlinks, emojis, slang. So there's a lot of things that can go wrong from a model's perspective and a lot of very unusual text. So what you'll often have to do in that case is clean all of that out of your data. So you might want to replace emojis with a text token of some sort, or just remove them outright. There's also a misconception that the more data you have, the better. And you can throw as much data as you want at a machine learning model, and you don't want to do that for two reasons. So first off, we have something called the curse of dimensionality. Basically, if you have too many useless inputs, they're going to swamp out the useful inputs we have simply due to noise. And it's also the case that the more data you have, the slower your models are going to be to train. So what you'll often want to do at the end of your pre-processing process is to score features based on one or more metrics and perform some form of feature selection. And that's usually an experimental iterative process. So you'll take the top 10, top 50, top 100 input features you have available and see how your model performs based on that. Okay. In most of the data science projects we have, that there's often a concern about the volume of data that we have available. So that there are ways of artificially enlarging the data that we have available. So what we often do is something called data augmentation. So if it's, we'll say, image data, and this could be patient x-rays, products on a conveyor belt, or in this case, cats, regardless of what kind of images you have, the steps you can do for this are going to be pretty much the same. What you'll do is you'll take the images you have in your data set, you'll duplicate them to create new instances. And for these new instances, you'll do random transformations. So you'll move objects in an image. You might make some small color changes, do some rotations. You might crop the image and then resize it back to the expected format. So what you can do is you can increase the size of your data set. And as a side effect, it should hopefully make your models a bit more robust because of the noise that you're after injecting. So the idea is you want data that's slightly different from what you have already available, but not too different from what you expect to see in the future. And it's a very delicate balance to get right. Okay, so once you have your data and your data is formatted and processed in a way that's consistent, you need to decide what kind of models you want to apply to your data. So the type of models you use depends, first off, on how complex the data is, how big is your data set, and what it is you're trying to achieve. So for very, very small data sets, or for data sets that are very regular, you might start with just some static thresholds or simple rules. If this condition is met, trigger action X. But that's going to struggle for any data set where the data is volatile or very changeable. Statistical models are a step up in that regard because they can be a bit more adaptive. So a statistical model could be something as simple as a rolling average, or it could be something a bit more complex, like an ARIMA model, for example. Even then, you are going to have a problem if your data set is particularly volatile, in that you're going to have to reanalyze your data set and refit your statistical models periodically if there are any dramatic changes in the data that you get available. So this is one of the big advantages of artificial intelligence models. So not only are they complex enough to be able to handle image and text information, AI models, they're also adaptable in that you can do something called continuous learning. So you can feed data as it becomes available into the model, and it can evolve over time. So just to give you an example of where your simpler methods might fail, here's a time series segment. Now this happens to be CPU utilization on some remote server, but it could be anything. It could be stock prices, social media activity, sensor data, whatever. So what happened in this particular instance is they had two programs running on a remote server. We'll call them program A and program B. And between program A and program B, When A stopped, we had an outlier that occurred at some odd transitionary period. In this case, it's called a level shift, because the distribution of values between A and B is dramatically different. So the average value and the distribution of values is very, very different. So let's just say we wanted to do anomaly detection, and this is the time series that we had available to us. If we were relying on static thresholds, that works well right up until program A stops, and we would have caught this outlier here and this large spike. But once we start program B, the thresholds that we have in place are no longer appropriate for the data that we have. Somebody's going to have to manually readjust those. And that's a big problem with static thresholds, and why machine learning is becoming more popular for a variety of domains, simply because it's powerful and it's adaptable. So I mentioned you can do something called continuous learning. What also makes machine learning very effective in practice is that we can do something called transfer learning. So online, there are a lot of models available for downloads. They're free, open source, and they're models that have been trained on very large data sets for long periods of time. So this is especially true for image classification or working with images in general. That tends to be very computationally slow and expensive. So you can use these pre-trained models and repurpose them for your own projects, and that greatly speeds up the project delivery date. So there's a very well-developed ecosystem for all of this. There's a lot of libraries available, and most of these libraries are also free and open source. So ML and data science practitioners, they're going to be using these libraries fairly extensively, and it allows you to create custom solutions for whatever your project is. Once you have your models in place and you decide to start running your experiments, you'll need to make a decision about where you want to run those models. Your first decision is probably going to be to run them locally on your own servers or machines. And that's probably the best place to start, because while you can run them on cloud providers, they tend to be very, very expensive for data science. So while cloud services, they are very convenient, they're reliable and scalable, and they're very appropriate for web development. One concern that you need to bear in mind for data science projects is that they can be horrifically expensive if you want to run a very large amount of models on a very large data set. What a lot of our clients do is they often use hybrid approaches. They'll often deploy most of their web services on cloud providers, but they'll train models on their own machines and then upload those pre-trained models to the cloud, where their final deployment is. At the other extreme, then we have something called edge computing. So this is something something John mentioned in his presentation. While you can train models on edge devices, there are some constraints that you're going to have to bear in mind. So this is an example of one device I've worked with myself. If you've looked at microcontrollers before, what will probably stand out is the massive heatsink on this device. So it has its own GPU, and that's why it has its own heatsink, and it is designed for training models. But even with a device like this that's specialized, you're still going to have fairly strict limitations in memory. You can't store very large data sets on these devices, and even then, training models tends to be somewhat slow compared to a dedicated server. So it's only really appropriate for fairly small amounts of data or fairly small models. Another issue with these devices is that you're typically only looking at sensor data in isolation. If you need to examine a lot of sensor data together, it probably makes more sense to do that in a centralized location on a remote server. The one case where you might have to use these devices is if you have very poor internet connectivity. So on a lot of factory floors and that kind of thing, you can't guarantee that your device will always be connected to the internet. In that case, it might make sense to actually run your model locally instead, especially if it's for some critical systems from a health and safety perspective. Okay. So just to give you some examples of some of the projects that we've done a number of cybersecurity projects, and these usually tend to revolve around anomaly detection using AI, and in particular using something called machine learning. So during these projects, the concerns that we typically run into most often are where to get data and how to analyze it. So getting a source of regular internet traffic, for example, is pretty easy to do, but getting sources of data where somebody has actually figured out which traffic is completely benign and which traffic is actually belongs to attacks is almost impossible. It's very, very difficult to find that kind of data. You can simulate it, but it's hard to find genuine data. We also run into problems when we define what an anomaly is. So for a lot of problems, and this doesn't just pertain to cybersecurity, but for most kind of anomaly detection problems, it's actually really hard to define for time series data which points you want to consider an anomaly and which points you want to consider normal behavior. Some anomalies are obvious, but others aren't, and it can make it a bit more difficult. One aspect that also makes this a bit more difficult is that the traffic that we're going to be seeing in coming years is actually becoming more inconspicuous. So you can use AI to try and make attacks appear more like regular traffic until it's too late. And this is one of the important aspects of using machine learning for anomaly detection, in that a while ago I mentioned that machine learning models are more adaptable. They're able to do continuous learning. This is something you need for cybersecurity projects because the traffic that you see incoming is going to be changing and changing very, very regularly. So I've mentioned machine learning a number of times. It really needs a talk in its own, but just to give you a brief idea of how it works, when you're conducting machine learning, what you'll do is you'll start off with a model and you'll usually just give it random parameters initially. The model is then exposed to data, the model makes predictions, and based on how good or bad those predictions are, the model tunes itself. So it learns in a very literal sense, which has pros and cons. So the good aspect of that is that it's automatic and you end up with something that's able to make very, very accurate predictions. The problem with machine learning models, and this is something John mentioned as well, is about explainability. It's very hard to explain how some machine learning models work. So simpler models have a small number of parameters. They're easy to understand, but for very large models, especially with neural networks, they can have up to millions of parameters. So it's pretty much impossible to explain at a low level exactly how they work. So you need to be careful about what kind of data you give to these models to make sure that you aren't injecting bias or you aren't giving it data that's not representative of what you're going to be seeing in the future. Because the machine learning algorithms really are a black box. The quality of the data that you give in really dictates how well the model is going to perform in the future. Okay, so just to give you an example of what we do for a lot of anomaly detection projects, when it is difficult to define exactly what an anomaly should look like, what we often do instead is do something called anomaly scoring. So we apply scores to data instead of a label. And what that allows us to do is it allows us to rank data based on how anomalous they appear and simply show that to the user. And the user can decide then what they want to flag as an anomaly or as a threat or as a problem and what they want to ignore. So in this slide, what we have are three variables. We have pump pressure, atmospheric pressure, and battery charge on the left-hand side. And on the right-hand side of the slide, we have the corresponding anomaly scores for these three input variables. And what we can see is the anomaly scores tend to spike when we have unusual behavior in the raw data itself. So this provides us a pretty easy way to visualize how anomalous certain data are and how we can present that to end users. So just to give you an example of another type of project that we've done, and this is something that Anne will go through in more detail in the next presentation. We can also use AI for decision and analytics. So AI is normally associated with you feed the model data, it makes accurate predictions. And that's something that machine learning is very, very good at. Machine learning is pretty bad when it comes to decision analytics problems. It's usually not an appropriate modeling method. But there are families of algorithms in AI that we can use instead. And I'll explain more about that in the next slide. So these help us with problems that are very, very large and very constrained. So it's often used for timetable scheduling, asset scheduling, that kind of thing. On a side note, for this project, where we worked on using AI when we use AI to schedule the charging and discharging of industrial batteries, the project entailed working with multiple teams at the same time. So we had hardware, software, and data analytics teams both working together. And one thing to bear in mind in these kind of projects is that there is a lot of overhead involved the more teams you have. They use different jargon and they have very different priorities. So for example, the data analytics team typically will want data as soon as possible because they can't really commence their work in earnest until that data is available. Whereas your hardware engineers are going to want to make sure that they're collecting data reliably and safely first. So you have different priorities, and that's something you need to be aware of. So I mentioned that we can use optimization algorithms instead of machine learning for problems such as decision analytics. There are a number of options available when it comes to doing optimization. Some of them are inspired by nature. Others are constrained to linear programming. Just to give you an example, on this slide, we have an example of genetic algorithms being used for a simulation where researchers are trying to train robots on how to walk. So how genetic algorithms work is that you start off with an initial population of robots. They're probably not going to be able to walk very well. The best robot in generation 1 is able to make one step and then falls over. But what we do in genetic algorithms is we take the top performing instances of each population, and we use them as a seed to populate our second generation of robots. So we take the top performers, copy them over, and we do something called crossover, which is roughly inspired by how reproduction works in nature. And we add in some random mutations for the sake of exploration. So what that allows us to do is it allows us to increase the average performance of these generations over time. So at generation 1, the best robot isn't really able to move at all, whereas in generation 921, the robots are able to walk in a fairly convincing fashion. It looks like they're able to walk indefinitely. Okay. So that's the end of my presentation. Thank you very much for listening. Aidan, so will I wait until after Anne's presentation for the questions? Or?
Exactly,
okay,
yeah.
No
We'll take questions
right.
for yourself, Christian, and then after Anne's presentation. But just to thank you for an excellent presentation, very practical and step-by-step overview of data analytics and visualization, and no pun intended, but it does give you a kind of you start to visualize how one of these projects would be implemented, and the different issues and elements that are contribute to one of these projects. So that was excellent.
Thanks, Aidan.
So I'm going to now introduce Quang-An Fan, who is a researcher at the Nimbus Research Center with interests including renewable energy, microgrids, energy management, and system optimization methodologies, and currently forms part of the data analytics team with Nimbus, with expertise in Python, MATLAB, battery modeling, parameter forecasting, system scheduling, microgrid optimization, and AI trustworthiness, and holds a BEng in electrical and electronic engineering, a master's in electrical engineering, and a PhD in energy management from CIT, with a thesis on developing optimization methodologies for a microgrid integrated with renewable energy sources and auxiliary battery backup supply. So, Anne, if you want to start sharing your screen, I'll pass over to you.
Hello.
Yep, that's great. We can see and hear correctly.
Yeah, thanks, Aidan, for that kind of introduction. So today I will present the data analytics applied to real-world research and industrial applications. So let's start with an outline. So my presentation will focus on 2 recent projects of Nimbus. The first one is the battery optimization system controller we call Bosco. And the second one is a predictive control system we call PCS. So now we are going to look at an overview of Bosco. So you can see here is the a PV system. Like we have a many panel, one face on the east and one face on the west, and the power of the PV system is about 10 kilowatts peak. On the right, on the left side here, we have 2 battery system. One is BYD lithium-ion battery units, and the other one is the aqueous saltwater battery. So the power of the batteries is about 10 kilowatts peak as well. So you can see on the right side here is a controller that we developed to control the system. And that's the aim of the project. So how we try to operate the system with a PV system here and the battery here. So you can see here is the testbed configuration. and the hardware highlight high level system overview. So our test bed is connected to grid. So we can buy electricity from grid, or we can sell back electricity to the grid if we have more than we need. So all the system is was installed and is located alongside the Nimbus Research Center on the CIT campus, and is now turned to MTU campus. This is a more detail of a schematics of the system. So sorry. So as you can see from the screen here, we have a Bosco controller with the 4 main inputs. The first one is the solar photovoltaic panels. The second one is the grid. The third one is the load. And the last one is the battery bank. So obviously, we cannot control the output power of the photovoltaic system, because the photovoltaic system depends on the weather condition. So the amount of energy from the solar system will depend on how much irradiance we have and how the temperature is. So we cannot control Irish weather. I think so. So we cannot control the electricity price from supplier, because we are customer and we need to follow their price. And also we don't want to change the operating schedule of the load. So we cannot ask the staff to go to work at 6 a.m. or go home at 8 p.m. So we will respect their working schedule, so we don't touch the load. So the only thing we can control is the battery. So how we control the battery bank to make sure that we can save money, we can reduce the bills every month. So that's the objective of the Bosco project. So as you can see here, this is the input data of the project. On the left side here, on the top, we have a 2 curve. The red curve is the energy from the PV system, and the blue curve is the energy demand from the building. So we can see that from 0 a.m. until 2300, we have 24 values of load demands and energy from the PV. So there are some moments we have more energy than we need during the midday lunchtime, from maybe from 11 to 1 p.m. We have a lot of irradiance, so we have more energy than we need. Meanwhile, in the early morning at from 8 a.m. to 10 a.m., all the staff go in the test beds, and we consume more energy than we can produce. So the thing is, if we need more than we have, we need to use energy from somewhere. And if we have less than we need, so sorry, if we have more than we need to sell it to somewhere. And if we have less than we need to buy it from somewhere. So we need to buy it from the grid. So whenever we purchase electricity from the grid, we need to consider the price. So here is the price from the grid. So you can see that the price, these are the sample of price that I take from the CMO company. So normally we have some peak here at 8 a.m. when everyone use the equipment for when they wake up, and also at 6 p.m. when they turn on all the equipment in the kitchen to cooking for cooking. So we need to decide when we are going to store energy in battery, and when we are going to take the energy out from battery to use. So what is the objects of the project? So we need to we want to reduce the operating cost of the building through the way we use the battery. So for the next 24 hours, so you can see here we have the 24 interval in the next 24 hours. from 0 until 2300. So 24 interval here, and we need to decide when we are going to store energy and when we are going to use the energy. So when, where, and how much we can use the battery, or we can't, or we want to off the battery. So it depends on the way we use. So what is the solution? The solution is the first step. We need to build on the model for the input data. So the model we need here is we need to build the model for the temperature. The second model is we need to build a model for the PV output data, and also we need the model for the load. So on the model here, we need to use the historical data. The historical data, in this case, we collect from the on-site Bosco controller. That's when we have a sensor system that we install in the test bed, and then we record all the historical data from the controller. And the historical data will send to the model here to build the model. And the methods we use to build the model is the AR. That's Chris mentioned above. So we have three models: temperature, PV outputs, and load. So when we have the model, that means we can know exactly what happened in the next 24 hours for the load and for the PV. And also we know what happened with the electricity price for the next 24 hours. So what we do next is we will try to generate a charge and discharging schedule. So the charge and discharging schedule will have a 24 value, and 24 value will be filled in the 24 interval. Like you can charge or you can discharge at any interval with different values. So the size of the population will be very huge because you have a 24 space with 3, 4, 5 value you want to fill in. Maybe you want to charge at 10%, you want to discharge at 5%, you want to charge at 20%, or you want to discharge at 10%, or even you don't want to use the battery. So you have a many variable to fill in a 24 slots of interval. So the size of population is huge. And because of the size of population is huge, so we cannot use the basic methods. We need to use a method look like a global optimization methods. In this case, in this project, we use the meta-heuristic methods. And the methods we use in this case is genetic algorithm to generate the initial population for the charge and discharge schedule. So when we have that schedule, we will, based on the schedule charge and discharge, charge 10%, discharge 10%, charge 20%, discharge 10% at any interval, we're going to calculate the state of charge of the battery. So SOC1 until SOC24 to make sure that the battery is not empty and the battery is not full. So when we have the value of SOC and we have a values of charge and discharge rate, we will calculate the amount of electricity stored in the battery or released out from the battery. I call EB1 until EB24. And based on the amount of electricity stored in or released from the battery, we can calculate the amount of energy we purchase from the grid or we sold to grid. So based on that amount of energy, we can calculate the cost for each interval. So we have a 24 interval here from SP1 until SP24. So the total cost for the next 24 hours will be the sum of 24 value here. And based on the cost of a day ahead, we decide which schedule is the best schedule among the population that we use GA to generate. So that's the method for the Bosco. And here is a simple result that we got that from the test bed. You can see the relationship between the voltage, current, and temperature when we measure from the test bed. It will be not linear like in the theory, but it reflects that exactly the value we want to put it in. So we we can control how much we can charge to the battery and how much we can discharge from battery. So the key things in this methods is how to calculate the SOC, that means the state of charge of the battery, because we cannot overcharge the battery, and also we cannot let the battery be empty. But we will select the schedule which will try, which can help us to reduce the cost of the system. That's the first project. The second one is a project concerned to the water level of a quarry. So this project's name predictive control system, and we call that PCS. You can see here, this is the quarry, and the customer, they want to keep the water level in the limits because they want to use the quarry for the mining activity. So the water level need to maintain in the limits, not go too high and not go too low. And look at the quarry here, we can see that the water level will be affected by the rain, by evaporation, and especially by the water increase. That means if we don't pump the water out, normally the level of water will increase when it's raining, or decrease when we have too much, when the weather is very hot. So the water level will change depend on the weather. So what we have done for the project, you can see here we have two limits for the water level, the lower limits and the upper limits here. And you can see here in the figure here we have two curves, the black curve and the red curve. The black curve represent for the simulated, the predicted level of water, and the red one is the real one, the measured one directly from the quarry. So we need to make sure that the water level will not go to the lower buffer and also not go to the upper buffer. Otherwise, we need to regenerate the schedule of the pump. So the purpose, the aim of the project is to generate a pumping schedule in the next 24 hours to make sure that with that pumping schedule, we can save money for the quarry. That means we try to avoid the interval where the price of electricity is very high, and we try to pump in the hour that's the price is cheap, but the water level is always in the border between the lower buffer and the upper buffer. So we have a 24 value here, a 24 interval with only two values, pump on or pump off. That means this problem is very simple compared to the previous problem for Bosco. So if we want to pump, we just put it in 1, and if we don't want to pump, we put it at 0. So the solution is we have a vector of 24 values, 1 and 2, a binary combination between 1 and 2 for the next 24 hours. And the size of this one is 2 power by 24. So we have two methods to do, but we can use the basic methods because the size of the configuration is not huge. But in this case, we use GA because the customer want to develop this one. Maybe they want to pump 1 pump, 2 pump, 3 pump, or 4 pump. That means we can have a 1, 2, 3, 4, 5 instead of only 1 and 0. So we need to develop a GA algorithm for them to develop when they have in life, they have a more pump than when they need. So we use GA to generate the schedule for the pump. So 1 for pump and 0 for 1 for pump on and 0 for pump off. So when we have the schedule of pump for the next 24 hours, we will estimate the water level for each interval. And we need to make sure that the water level will not go to the upper buffer and not go to the lower buffer. And based on the water level and the pumping schedule, we will calculate the amount of electricity purchased from the grid only purchased from the grid. So we can see that how much we will pay for each interval and how much we pay for the next 24 hours. And we will have the best schedule for the pump. And this project already applied, and the customer now is currently use the solution we gave them. And this is the simple result from the graph now they have right now. We have the water level here below the 20 meter as they suggest. And we have a pumping schedule here. So some periods we will not pump, and some, I say this schedule for the winter. So we need to pump a lot of time to make sure that the water level is not going too high. And also this is the pump state, that means pump on or pump up. Okay, so that's the two projects that we were working on. Sorry if I were talking too fast. Yeah, thank you for your listening.
Not at all, and thank you very much. Another excellent presentation, and two projects that I think everybody could relate to, and the way you talked us through them, we can really see the different steps involved and the different elements that we need to take into consideration. So that brings us to our Q&A session. So we have, plenty of time. If you have questions, please enter them into the Q&A function. I'll kick it off by maybe just asking Christian and Anne,